Yes, I'm going to introduce to you the concept of something called maximum likelihood. This is a sort of generic and general principle that can be used for how to do statistics in general. And maybe for now in the basic stats course you will be used to doing different kinds of statistics, use t-tests or f-tests or chi-square tests, sort of around normal distribution models, you could say. Actually, there is a general principle for how to approach the way we do statistics, no matter what sort of the basic model or assumption about our data at hand really is. Let us make it a bit abstract and assume we are in a situation where we have n random observations from some distribution, from some density function, and density function with some unknown parameters, theta, as we would call them. There could be several thetas. So this could be a mean and variance in a normal, but it doesn't have to be the normal distribution. It could be in basically any kind of distribution, also discrete distributions, as we could exemplify later. If we assume that all of these assumptions is a classical assumption of independence, that is, that they provide independent information, each of those observations, then we may ask the general question with a general distribution and sort of general unknown thetas in such a distribution, how should we compute the theta? How should we estimate theta as a function of, then we're going to have a random sample from this situation, x1 up to xn. How should we estimate theta hat? What should that be? Well, we're going to estimate it with what we would call now the maximum likelihood estimator, the MLE. And what is the maximum likelihood estimator? So we're going to estimate that to be the maximum likelihood estimator. Well, what we are going to do is to formulate the likelihood function. The likelihood function, which is the function that basically expresses the joint probability density of the set of n observations. So we take a probability approach and say, what is the joint likelihood? What is the joint density, the joint distribution here? Well, the joint distribution, we would typically call it, it will depend on the underlying theta, it will depend on the data, x1 up to xn, and it will be, since we have independence, the product from y up to n of each individual data point here. That is a basic sort of multiplicative rule for independent data, that the density function, the joint density, will become the product of the individual densities. If we have this, we are going to find the value of theta that gives the largest possible likelihood function, value of the likelihood. So we are going to see this probability density, this joint probability density, as a function of the unknown parameter where we have the data plugged in. Really, it's a density for the data, you could say. But now given the data we have, we try to find the theta that is most likely given the data we have. So we find the theta that maximizes the likelihood function. So we use the probability distribution at hand to find the most likely value of theta. The way it's usually done is to actually use what is known as the log likelihood, and then we may suppress really the dependence of the data, and then that would be the log of the L, which then turns this into a sum. The log of a product is the sum of the logs. So we have, I used log here for the natural logarithm actually. So the log of each f of xi, that would be the log likelihood function. And this one can be used for statistics. So as I said, theta hat, the maximum likelihood estimator, if we is precise, theta hat is the maximum likelihood estimator if theta hat maximizes the log likelihood, or equivalently the likelihood function. So in all cases we would go ahead and write this likelihood function up and then do this maximization thing to find theta hat. Actually, having done that in general, so this is a very generic approach that tells us how to estimate something unknown, theta. There are certain properties of this approach that are nice, very generic properties. Actually, there is a consistency property. Consistency. This means that theta hat estimated on n observations will tend, actually I should be precise and call it, it's asymptotic consistency. The fact that theta hat maximum likelihood estimates will always, for increasing number of observation, tend to the right thing. Many of our observations already do that, the thing that they are actually unbiased already. But however, another thing is that we can't do, I mean, I'm just going to sketch the idea of this. I mean, you could spend a whole course on likelihood theory, actually, which is a good idea at some point in your future, but for now I'm going to sketch the idea. So I'm going to be loose on and just mention some things. We can actually do confidence intervals, and we can do hypothesis testing based on likelihood, the likelihood approach. Confidence intervals could come as follows. A confidence interval would be actually all those potential thetas, I use this for the possible values of theta, which has a certain likelihood, capital C. So if we set up a certain level there, we could compute confidence intervals based on the likelihood principle alone. These confidence intervals may actually in some situations have quite good properties, but that's for another course, another day. I would maybe the hypothesis testing approach, let me dwell on that because there is an interesting link to the kind of the traditional statistics we might use in this course, the t-test, the f-test and things like that, coming from the normal assumptions. There is a general principle for doing hypothesis testing. What if we have very generally formulated the hypothesis that, that the parameter belongs to some subset of the original? We have the alternative is kind of the general, that's a big set. There's a big set of potential values for theta, and then we have a null hypothesis, which is a general one, which is a smaller set. It could be a single value, but it could also be actually a set of potential values smaller than the general model set in the outset. Now, such a hypothesis test could be tested by finding the maximum of the likelihood function under the assumption that we stay within the null hypothesis. So we maximize the likelihood function within the constrained null hypothesis set, and then we compare it with the maximal of the likelihood function under the general model, I mean the full model. So, and that will be a larger, because that is maximized over a larger set. So we take the most likely value of theta under the null, we compare it with basically the likelihood of the most likely value of theta under the the general model, and then there is a classical asymptotic result which is used to make this operational. If this is called Q, actually, usually. If we look at not Q, but if we look at -2 log Q, if we transform it with the log like this, such a statistic will, at least asymptotically, under certain assumptions that is often fulfilled, will follow a chi-square distribution with a degrees of freedom f, which is the difference in dimensions of these models, the dimension of the big model minus the dimension of the smaller model, the null hypothesis model. So, asymptotically, as approximative, this is okay. So we can do hypothesis testing on general thetas in all kinds of models in this way by computing this and using a chi-square distribution to do the testing. So this is a very generic principle for doing hypothesis testing with one weakness, that it's only an asymptotic and approximative result. So n needs to be sufficiently large. Then what about what we do in our course on a regular basis, f-test, t-test, regular kind of test like that? In such test in our course, in this kind of a basic course, tests in a basic course is often based on what we may call linear normal models. That's a general term for many of the models that we use in a basic course. Models that assume certain level of linearity and normal assumption on parts of our data. In linear normal models, we can actually show that if we, even though we don't do it explicitly in what I tell you when we compute means and variances and t-test and f-test and blah, 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 I don't talk about maximum likelihood there. But we could do maximum likelihood based on the normal, actually. And if we did, and if we found the -2 log Q for such traditional tests that I've shown you or showing you in this course, we would see that this -2 log Q, the likelihood ratio test, as it's called, the likelihood ratio test, would in fact be some function of V, often, where the V is something that has an F distribution with typically F times F as defined as above times the dimension of the basic model in the denominator. So the fact is, this means that we can do statistics which is equivalent to the likelihood ratio test, but based on the exact F distribution rather than the approximate. So when we do t-testing, f-testing, sometimes an f-test may be the same as a squared t. So all the methods that you're taught as basic methods, without mentioning likelihood methods, really are likelihood approach also, but it's a better way of doing likelihood than the chi-square testing. So it's just giving you this link that what we do in a basic stats class really is also likelihood based, even though we don't need to know it and we don't need to use this general way of thinking and principle to actually understand it and do it. This was just part of this lecture to introduce this general idea of likelihood and telling you that what we do usually actually falls within this general way of approaching statistics. Thank you.